Hello, and in this video, we will be talking about systems of equations that are consistent and inconsistent, and also those equations that are dependent and independent. So let's look at a few terms here. Feel free to take notes, and we're going to talk about first a system of equations that has at least one solution. And that system of equation that has at least one solution is consistent. So a system of equations that is consistent has at least one solution. Okay, for example, so if you have a system, two equations, two unknowns, right? And you have a graph. The graph say it has my x and my y. Say it may look something like this in nature. Say it looks like this. As you see, this will be an equation. This here, and this also here will be an equation, right? That's graph. And somehow this here at the middle part there will be the solution wherever it intersects at, wherever it's intersecting, right there. Excuse me, this is my first time of using this stylus pen. I usually use the whiteboard, and all my subscribers usually see me as I'm teaching in real time on a whiteboard with whiteboard markers. This is the first time I'm using this system, so I'm getting used to it. But this is consistent because wherever it intersects at, the two lines on the graph intersects, that is one solution. This is one solution. And your one solution is your x coordinate and your whatever your x coordinate and your y coordinate is. Okay? So whatever your x coordinate and y coordinate. This is graphically speaking, right? Basically. Now you can actually, if you have two systems and you use substitution method, or if you use the addition method or elimination method, you can solve the two systems or solve the system of two equations and two variables and use back substitution. You will find that one solution where it intersects at. But we'll talk about in the later videos. Okay. Also, you can also uh, use the system, okay, and set them up as a matrix, and also use various techniques like Gaussian elimination or Gauss-Jordan elimination, Cramer's rule, all different types of different techniques in solving the system. We'll get into that later on. So a system of equations that is inconsistent has no solutions. Okay, and so an example of that is if we have a systems of equations, two equations, two unknowns, and say it does this, a line does this, and a line does that. Well, look what happens. What happens is you have two parallel lines. As you know from algebra, if two lines have the same slope, those lines are parallel. And so this will render no solution because the two lines will never intersect. So this is no solution, but guess what? It's going to be inconsistent. Everybody see that? Take a few minutes and pause the video. You pause the video and then you could pause the video and take notes, and we'll go to the next couple of sets of terms. Make it sound better. System of equations. And two unknowns. Two unknowns. A system of equations with two equations, two unknowns that have infinitely that has or say that has infinitely many solutions dependent. And then a system of equations with two equations and two unknowns um, that has one solution or no solution are considered independent. There we go. Okay. So a system of equations with two equations, two unknowns, uh, has infinitely many solutions are considered dependent, and the systems of equations with two equations, two unknowns that has one solution or no solution are considered independent. So we'll do a couple of examples to show this. Take the time out to pause the video and take some notes on this. So let's look at some examples here. If we have a graph that looks like this, All right. And then, of course, you know, the graph will look so. This is only a sketch of these things. So you got a graph that looks like this, and a graph that comes across, say, this way, with a point right smack in the middle there. Okay. We'll say that this graph here is y is equal to 3x plus 2, and that this graph here is y is equal to negative 1/2 x plus 1. So this here, as you can see, and let me see if I can choose a different color if this doesn't mess up on me this time. If we look at this, um, let's see if we can use a red. Okay, see if we can use a red. So here, and it works. This will be one. This will be one solution. This will be one solution. And the graphs here, what? The graphs intersect. The graphs intersect. So therefore, the system is what? Is consistent. And since it has at least one solution, the equations are independent. Okay. So that's one way in looking at this, if you will. And then let me show you another example. Say that we have another graph. Let's put this graph up. Let's use this. Go back to my blue for a second. Still marking red for some reason. Still giving me red. Okay. Well, now it's giving me blue. All right. So this is X and this is Y. And supposing we have, this time we have two parallel equations that say they have positive slopes, just like this. And these are just sketches, not necessarily the scale. And this is y is equal to 3x plus 2, right? And then this one here is going to be y is equal to 3x minus 1. As you see, the slopes are the same. Slopes are the same. So you have two parallel lines, and they'll never intersect. So if they never intersect, there'll be what? No solution. Be no solution. The graphs are parallel. Graphs are parallel. What else? And the equations are independent. Okay? Equations are independent. Everybody see that? So here, as you know, when you this is shown graphically. You can also since these two equations are in slope-intercept form, you can actually set them equal to one another, and you got variables on both sides. You can solve for x, right? And once you solve for x, you can back substitute and then put whatever x is and solve for y and get your point of intersection for this one. But this problem over here, if you set it equal to y equal to, you set the equations equal to each other, then what's going to happen, you're going to wind up having a number, different values equaling to each other, different values. It's not like 2 is equal to 2 or negative 5 is equal to negative 5. That could be considered as something that is infinitely many solutions. But if you have 2 is equal to negative 1, or 0 equal to 5, or negative 5 equal to 10, then you know that that is no solution, and that if those two equations that were graphed, they will be parallel, and it will render no solution. So this, these equations are still independent of each other, but um, but it's also inconsistent. Now I forgot to put inconsistent. This is inconsistent. So let me write down here. I forgot to mention. Um, let's put it right here. Um, semicolon. The system is inconsistent. Okay, so the system is inconsistent. Okay, so let's take some time, uh, pause the video, and copy these notes down, and then we'll talk about the last example here. Okay, for the last example, I want to show. Oops, sorry, folks. Let's try that again. Now, so let's do a graph. This graph shows like this straight line. Now, it's actually this graph that I'm showing you actually overlaps each other. So if we say that this is 3, not 3, but let me go back. Okay, let's say that this is 2y is equal to 6x plus 4, right? And if this is y is equal to equal to 3x plus 2. Now, if you actually solve for y here, if you actually solve, these are two different graphs, but they're the same. It's just that they overlap each other. If you actually solve for y, you're going to get the same thing. So remember I said when you set these two equations equal to one another, because they are in slope-intercept form, and then you solve for x, you're going to end up getting some sort of identity solution, right? Which is going to be the same solution. So this is why it's infinitely many. So here we're looking at this, and this here will be infinitely many solutions. The equations have the same graph, and the system is consistent and the equations are dependent. They're dependent on each other. So this concludes the short lecture on systems of equations that are consistent and inconsistent systems, and that the equations are independent or dependent. Stay tuned for a short part two to this because we'll do some short examples.